Okay, so we have defined our model. Let me just say what we have done previously here. So we solved the model, then we went to the post processor. We have plot some things. We have come back to the solution. We have defined that we are going to show things in the Gaussian points, and then we solve again, and we show again the solution of the equivalent stresses in the elements. Okay, so somehow that was the first introduction how to define the model. Now we would like to do this model but in a parametric way. What means that? We are going just to copy all of this. I'm going to create a new file, and here at the beginning, before defining all those things, I'm going to write a command: define parameters. The way that we define parameters in ANSYS is with this command, this start set, then we define the name of the parameter. So for example, L beam is going to be our length of the beam. We have defined something which is equal to 50, so we will put 50. We can just copy this set to define now the height of the beam, which we're going to use 10. The width of the beam, which we are using 2. I'm just defining the parameter that then I will replace in the next steps. So LHB yielding Fy equal to 23.5, elasticity equal to 21,000. What else? The load. Load P. We define the load P according to this equation that we have here. We can do the same here. We can define that this is going to be h of the beam times h of the beam times b of the beam times Fy over 4 times L of the beam. Now, previously we saw that this load is not fully plasticized in the section, so I'm going to increase the load by 50%, 1.5, to see what happened in that case. Okay, so now I can just go to the model and change the thing that defined the model. So for example, this length of the beam was defined here when we have defined the nodes here and here. The edge of the beam as well is here and here. The yielding capacity is almost at the end of the modeling. Let me remember where that was in the material part. Here, the yielding, and also the constant here is B of the beam in the thickness of the plate, and the load was defined after this. Here, define load. This was the load that we have applied in the direction Y. Now we're going to apply that in the negative direction. Load P. So we have created some parameters in the model. I'm going to also arrange something here. For example, here in the solution, this comment I'm going to put it here up, and also what I showed you regarding the extrapolation of the result. I'm going to put that here as well, and I'm going to delete the rest. Wait, and we need the solve command. Modify example. I should call it parameterize. Okay, so somehow I have parameterized the model by defining the parameter here. Now I can just copy everything from this point down, Control C, and I can paste that here. But first, let me just clean this model that we have here. I can go to File, Clear, and Start New. Do not read any file. Yes. Somehow we are back to 0. So this thing that we did previously, now I have modified certain things. I can just copy them, paste them that here, and you will see how the model is running immediately with the parameter that we have defined. Close, and we can just go to the post-processor element solution von Mises to see again the plot of the stress distribution. Again, the section is not fully plasticized. We can just increase the load even further. But wait, I'm a little bit surprised about something. No. Let me see. We can just click here as well, and instead of watching to the equivalent stress, we can see the stresses in the x direction. And we see here, which is the negative, which is the blue part, and the positive, which is the red part. Here the stresses are bigger than the yielding because this is not the equivalent stress that is restrained to 23.5. This is the X component. The X component is combined with all the other stresses for reaching the plastic state. So again, the the load is somehow not reaching what we are expecting. Now I want to check if the load that I have applied is the one that I was expecting. So 23.5 times 1.5 is supposed to be 35. Let me see. We can just go to here, list, load forces on all nodes, and we see the force is 23.5. So why is that the reason? If I thought that I modified that. Minus P load. That is something. There is something not actually working here. Let me see. Parameters. Yes, scalar parameters. Load P is 23.5. Okay, there is something that I didn't define correctly in this case. 50, 10. Okay, anyway, maybe we can just copy this again and define that the load is going to be 30 kilonewton immediately. I don't know why that didn't work immediately. Okay, so we close this, we clear the model again to run it once again. Another thing that I would like to do is to define the discretization. We're going to define here set horizontal divisions and vertical divisions. So we will go to the match bar, doing the match, and here this horizontal division and vertical division, we're going to increase the match to horizontal 50 and vertical 10 to see now how the model looks like when we define things in that way. Let's see again. We copy everything, we paste that here. You see that the match, in this case the node have changed. The load is applied in a different node because of the new discretization. So it would be better to actually apply the node in a key point instead of the node. Okay, so we are going to again clear everything. And at the moment of applying the load, here f item, let me just boom. I'm going to copy thing up to that point. Define parameters. We are going to go to the preprocessor, loads, define loads, apply on key point. We're going to select the key point that we have there, which we know is going to be always the same number, and we are going to apply the load in the direction Y. Oh, sorry, I'm applying a displacement force on key point there. Okay, force in Y direction with a value of 222, just to see then how that looks like if we save this as a script. Example 1 commands version 2. I can go there to open this version 2 of the command and see how that last command looks like to replace that in the script here. So it's basically, first we have selected the thing for doing a displacement, but actually we wanted to do a load, so this is F on key point, something like that. So I'm going to copy that in our modify script here. And I'm going to modify that here. And this is supposed to be load P. So in this case the load has already been defined, so we can just work with this. I can just run the next steps in this case. Let me just see something about it. To delete this thing which is related to the previous case. So here we move then to the boundary conditions and to the analysis. Boundary conditions and analysis. So now you see that the analysis run up to that point and it stopped. So we can go to the general post-processing, read results by pick, and you see that the result reached this point 11. We are not reaching the full loading, we are reaching a load which is smaller. We can just read this point, close, and then plot the results. Element solution for Mrs. Stress. We see now how the plasticization is bigger in this section. What happens? The load that we are applying is bigger. I define the load as 2 122, and somehow instead of 100 steps we reach 11. So 11 over 100 multiplied by 222 is a load equal to 24 kilonewton. So closer to the 23.5 that we have defined previously. Okay, so I'm going to stop the video here again, and then we will continue with further analysis.